Alright, so the question asks, I'm just going to read it. Define potency using the diagram. Using opioid as an example, describe and illustrate with graphs what you understand with the term potency, efficacy, partial agonist, competitive agonist, therapeutic index. So even though that's all the question, we're going to have to define a lot more things. So you can either draw the diagram first or you can define it first. But let's draw the diagram first. So this is a graded dose response curve versus concentration, which is a log scale. And so you should say log dose is the x-axis. The y-axis is response percentage of maximum for full agonist. So this is 100% efficacy, right? This is 100% full agonist. This is 50%, and so on. What is 50%? 50% is the EC50, which is defined as the potency. So you can say that potency is equal to EC50 on the graded dose, which means, what does EC50 mean? It means that with that dose, you get 50% of the maximum response. So the dose required for 50% of maximum dose. Now, ED50 on the quantum dose response curve is also potency. And what is that? That is the dose required to produce effect in 50% of the population. Okay? So it's 100% effect, but in 50% of the population. So anyway, so fentanyl is more potent. So what is the definition of potency? We haven't even got to that. The concentration of the drug required to produce an effect. That's it. So fentanyl A is more potent than B, morphine. Okay. Increased potency is determined by increased affinity and increased efficacy. So in simple terms, this is just a memory thing. Maybe I'll change different color. Potency A plus E. Okay, so potency is determined by an affinity and efficacy. That's why we have to define affinity. What is affinity? The best way I could describe it is using this diagram. This is affinity. So this is the ligand or the drug, whatever, and this is the receptor. So the tendency of the drug to bind to the receptor. So the tendency of the drug to bind to the receptor. The efficacy is a measure of maximum level response that the drug can produce, which is the Emax. So we can actually put here Emax, which is 100%. And then in full agonist is high affinity and high IA. What's IA? IA is the intrinsic activity, which is the measure of the drug. Again, the measure of the drug, or you can use this diagram, the measure of the drug that what? The tendency to produce a response once bound to the receptor. So the affinity is the tendency of it to bind to the receptor, while the intrinsic activity is a measure of the drug to produce a response once bound to the receptor. So full agonist is a high affinity and high IA, which is a 1. Intrinsic activity is a measure of the drug's tendency to produce a response once bound. Then you have partial agonist. So partial agonist is again high affinity plus IA. What did we say that potency was? It was affinity plus efficacy. That's what it depends on. And so agonist also depends on affinity and IA as well as the partial agonist. IE only activates some receptors. So fentanyl and morphine are full mu opioid receptors, but bup is a partial. So that's drug C. EC 50% reflects potency, the dose required to produce 50%. We already defined that over there. Competitive antagonist is it competes with the agonist at the orthosteric site. What's the orthosteric site? The same site, but do not activate receptors with no effect and is reversible. Example, naloxone with opioid at the mu opioid receptor. Antagonism can be overcome with an increased dose. Agonist to achieve an Emax. So you can say A on the diagram is fentanyl and B on the diagram is fentanyl with naloxone. So what is a competitive agonist? A competitive antagonist is something that binds at the same side of the receptor, which is the orthosteric site, but it doesn't actually it doesn't activate the receptor. Do not activate the receptor with no effects and is reversible. So it's just an antagonism. It just basically affects it. It competes with it. And then you have the quantal dose, because that's all the question asked. But obviously, they might ask other stuff, so such as a non-competitive antagonist. So here, a non-competitive antagonist, such as ketamine at the NMDA, that one binds to an allosteric site, leading to a conformational change that alters receptor activation by the agonist. An antagonist cannot be overcome by increasing the agonist. So it binds to a different site, okay, and you know that it's next to the magnesium plug. It binds to a different site than what the glutamate. It's the same with GABA. GABA binds on a different site, on an allosteric site, and causes an allosteric modulated change, right? So this is the same thing, a conformational change. So if you're confused about the term, no, allosteric is a different site. Orthosteric is same. And how do you remember that? The word orthodox, that's actually the Greek word ortho means straight. So it's the same site. That's actually the real definition. I just chat GPT'd it. Alright, and then the second part of the question was asking about TI. So a quantal dose response curve is a log dose and binary all or nothing response in the population. So an ED50 is the dose required to produce a response in 50% of the population. So an LD50 is the dose that requires to produce a lethal effect. And so TI is LD over ED50. So a higher TI means a widened TI, which is safer. So you have the therapeutic effect, you have the toxic effect, the LD50, the ED50, this is percent of the population, with absent, I can't read, with observed effect, and that's the therapeutic window. Alright, that's it.